Good day. You should find this sheet, How to Classify Chemical Reactions. It lists the 5 main categories of reactions, and we're going to go through it, but I'm going to go through it with a PowerPoint, but it'll follow in the same order, and it will be nutty. So, we want to be able to classify chemical reactions. It's very useful for a chemist to be able to classify reactions because often it gives an idea about how dangerous a reaction may or may not be. We start off with synthesis. Well, what you look for is on the right side of the equation. There's no plus sign. All you have is one compound. Synthesis means to put together. Now, synthesis involves forming bonds, and it is usually exothermic. It usually gives off energy. So here are some examples. You have 2 Mgs plus O2 becomes 2 MgO, and PCl3 plus Cl2 becomes PCl5. Now, one of those examples may be on your sheet, the other may not be, so you want to copy this out. But the bottom line is on this side, to the right of the arrow, on the product side, no plus sign. Same thing here, no plus sign. The plus is on the left. Whenever you see that, it has to be synthesis. Next one, decomposition. It's the reverse of synthesis. Instead of things coming together, things are breaking down. Instead of one product, there's only one reactant. So that means there's no plus sign left of the arrow. And if the other is exothermic, decomposition is usually endothermic. It usually takes energy to jiggle the atoms apart. So let's see what we got here. As usual, probably a couple examples. One you'll have, one you won't. And when we look at the left side, the reactants, no plus sign. No plus sign. This is one we want you to get used to. If you have a chlorate, it ends up being a source of oxygen. If we gently heat this up, we can get it to break, but not into positive and negative ion. It actually breaks right here after the chlorine, the oxygen comes out. And that's one you're going to have to memorize for predicting products. So, 2 down, synthesis, decomposition, reverse of each other. Synthesis, one product, decomposition, one reactant. Now you say, why do we have an activity series? And you should have a piece of paper that says activity series on it, hopefully in your package. If you don't, I'll have to post it. And what this tells you is the order of reactivity of these metals and then of the nonmetals. And what this applies to is for single replacement reactions. Elements that are higher up don't like being on their own. So lithium, for example, wants to be in a compound. Potassium wants it, but not quite as much as lithium, and so on. And when you get down to gold, gold likes being on its own. So if you say, boy, we've got this COVID crisis, lithium, potassium, calcium, they'd be really unhappy. They want to get together with other elements. Whereas gold, platinum say, hey, I'm okay on my own. I'll just watch some Netflix, listen to some music, and hang out. It's all good. Now for nonmetals, it actually follows in the order of the halogens. Fluorine's the most reactive. If you watch that crazy animated video, they locked away fluorine so chlorine could go to the dance. Fluorine is so reactive, or as they said, attractive. And that means fluorine can boot out any of the elements below it. So let's take a look at zinc. Zinc can boot out any metal below it. So if it sees any of these metals in a compound, zinc can replace it. But any of these metals, zinc cannot replace. Zinc cannot kick them out because it's not as reactive. And that's what it says here in a rectangle. And you may want to pause the video and copy it out. An element by itself can only replace an element in a compound if it is above that element on the chart. And this is the chart. And this is an amazing sentence because it had 3 2-letter I words in a row. So I was quite impressed by that. Make sure you copy that out. We're going to need that only for single replacement reactions right here. So single replacement, you can think of as a soccer reaction. You're kicking someone in the butt and kicking something out. Or people like to think of it, hey, nice school dance, and you have an element and a compound, and you end up with a different element and different compound. So the element by itself tries to kick out an element in the compound. And it says use the activity series to predict if a reaction will occur. Metals kick out metals, non-metals kick out non-metals. And that's because we're looking at ionic compounds and we want to end up with positives and negatives together. So we look at this one and we say, hey, here's potassium. Now we know potassium is way up on the chart. It's by itself and it goes whoomp. It kicks aluminum in the rump. Now aluminum's all by itself. Then the potassium and the chlorine get together. We got to remember our formulas, 1 plus 1 minus, KCl, and now it's all balanced. If we go the activity series, we see that K is above Al, and therefore the reaction is going to occur. We used our activity series to figure that out. Here's another example. Oh, isn't that nice? Yeehaw. Here's bromine, and there's fluorine. So the bromine's trying to get together the calcium by booting out the fluorine. So that's like you have a couple at the dance, and a gal comes along and says, hey, I'm going to cut in, and the fluorine ends up on her own, and the calcium and bromine are together. Now we have to look at our chart and say, would this actually happen? Well, bromine is below fluorine, so we're going to have to write down Norx. Norx, Rx means reaction, no reaction. And again, that's from the activity series, and it should do a little hop to celebrate. There it is. All right, so that's everything about single replacement. That's the only time we're using the activity series. Things get more complicated. We get down to double replacement. This is where you have a compound and compound becomes a compound and compound. So we're looking at two ionic compounds reacting to make two different ionic compounds. I like to call this the double date gone sour, and it's easier to show once we put down an equation. So the ions are switching partners, example. So I can't remember if this is the example you have or not. If it is, you don't have to copy it. If it isn't, you may want to copy it. So what we see is here is sodium, and sodium and chlorine were driving to the dance, and they had a big scrap because, hey, they disagreed about running a red light. And so they decided to break up. And silver and nitrate had a big argument on the way to the dance. And who knows why, but anyways, they split up. So that means they basically become single at the dance. So sodium says, hey, I'm going to get together nitrate, positive ion, negative ion, and makes sodium nitrate. Then we look at chlorine and silver. And they say, okay, well, we'll get together. And whoosh, they make silver chloride, and the formulas are correct. And so you say, okay, we have started with two compounds. We've ended up with two different compounds. Somebody's saying, hey, how come the Ag came before the Cl? Because the positive ion always comes first. I got to get rid of those arrows. Okay, boom. And let's see if we have a second example. And our second example, we got K. We know the K is going to get together the nitrate. Thump. And we know the I and the lead will get together. Thump. And we have to write proper formulas. It's got to balance out the charges. But this again, double replacement, double date gone sour. You remember that? It'll be a piece of cake. But now we have a special case for double replacement, and that's called neutralization. And if it's a neutralization reaction, do not write down double replacement or I will mark it wrong. We have to remember neutralization is when we have an acid and a base. They get together, they make a salt and wawa. And so in other words, the acid neutralizes the base, or the base neutralizes the acid. They limit the effect of the other. So it's the same idea. The ions are switching partners, but it's a special case. And you have to be able to recognize acids, bases, and salts. So we say here's our H. There's a terrible underline. And H and OH are going to get together. Oh, that's a terrible arrow. They're going to make WOA. In this case, it left the sodium and the chloride behind, and they make sodium chloride. And again, positive ion ahead of negative ion. So if you can recognize that you have an acid, H at the front end, unless it's organic, sodium hydroxide, recognize the OH at the back end, H and OH, they get together and make the water. And what's left behind will make the salt. Let's see, do we have another example? Helps to push the right button. So we look at this beast, and we see here's our H, and here's our OH. And there's our water. Here's our calcium. Here's our nitrate. And so, thump, thump, fried noodles. And there's our calcium nitrate. So again, it's a double date gone sour, but acid plus base makes salt plus water. Now you're going to say, well, what happens to the base and an acid? Same thing. What happens to the water and salt? Same thing. As long as they're on the proper side of the arrow. The acid and base have to be on the reactant side, and the salt and the water have to be on the product side. 4 types. Now we're down to our last type, number 5. Combustion, and it's really simple. Simply means a reaction with oxygen. Since it's a reaction, oxygen has to be on the reactant side. So we look at this and we say, hey, that looks like ethane. That's an organic compound. It combines with oxygen. We've balanced out our equation. And we've made CO2 and H2O. And that happens every time we make a combustion reaction. We make carbon dioxide and WOA. Now, how do we know this is combustion? Here we have O2 all by itself, and it's left of the arrow. If O2 was to the right of the arrow, it cannot be combustion. O2 left of the arrow. Let's try another example. Now, if we burn a metal or a non-metal, we're going to make one product. And this is combustion because we have O2 to the left of the arrow. Now MgO, they get together that way and we go and balance it. No sweat. So anytime we burn something organic, CO2 and H2O, anytime we burn a metal or a non-metal, those things are going to come together. And you're saying, whoa, hang on, that rings a bell. We only have one product. So in that case, the second example is also synthesis. And that means that's a chance to get a bonus mark. If you recognize something as synthesis and combustion, you can get extra mark. You better not write down synthesis for this because there's a plus sign. This one has no plus sign. So hopefully your notes are making perfect sense. And we're going to try that out with 15 examples on the next sheet.